Morning, folks. My clicky keyboards are working, so I know I'm live. Make sure I got a Teams window somewhere. Making sure I know what to say in today's lecture. Starting up in a minute. Good morning to you, everyone out there in internet land. Welcome to COMP2300 / 6300. And this is the second lecture of week 1, where we will be talking again about digital logic and continuing the discussion we had on Monday about what is the relationship between the logic that you might have learned in a class like Math 10005 and the CPU in your computer. So that's what we're trying to sort out in this week. I'm just going to make sure I've got everything ready. I've got my remote control thing, got my Teams window. I think I'm live. I hope I'm live. Make sure that, refresh that one, see that everything is going to plan. Offline? No, I'm definitely online. Don't tell me that, Restream. There I am. I can see that I'm online. Okay, so in that case, I'm safe to full screen my Teams on this computer so that I can see what's going on. Now, it's been an exciting week, and it should be exciting today for those of you who are having your first lab. What we've found is that we've changed to a new piece of hardware this year, the microbits aren't something that we used in previous years in COMP2300. So we're doing a lot of learning about all the different ways in which they can go wrong when someone is installing them on their computer for the first time. And I'm sure that you realize that everyone's computer is a little bit different. Everyone has slightly different setups. They've had different classes before. They've taken different things. They might have changed something, installed something extra, uninstalled something. So we're finding that there's lots of different interesting things that can go wrong. And there's 400 of you, so there's many, many computers out there that need to be looked after. We've got a great team of tutors who are doing a wonderful job helping you folks out in the labs this week. They've been helping out folks online. They've been helping folks out on campus here in Canberra. And I think that what we're finding is that, broadly speaking, everyone is getting this to work. So it's a week of getting things to work. It can take an hour or two to think out the problem and go through the steps carefully. That's why we've got a week 1 lab, and more often than not, everyone has been successful. There's a few folks remotely who I know don't have a microbit yet, and I would encourage you to use whatever resources you have to access one as soon as possible, because it's required equipment for this course. So you need to make sure that that problem is solved sooner rather than later. There's some very new microbit V2.2s that are coming on the market now, and I've heard of a very small number of people having one of those instead. They've changed something very small about how it works, and I've just ordered a couple from England to express shipping to us here so we can test it out and get those working as well. But overall, I'm seeing a lot of people getting their microbits to work, which is wonderful. That's the main task for this week in labs, just getting things to work, just installing things on your computer and making sure you're a bit comfortable with the tools. At least you've tried everything once. And we'll talk about tools maybe at the end if we have a little bit of time. I can talk about that. Now, what are we talking about today? Digital logic. Let's just go through the story so far, where I left you. We talked about Boolean algebra, which you've seen already in Math 10.05 or your previous courses. The idea of a number system made of just 2 numbers. And now we call those 0 and 1. We just used the 2 regular numbers from our counting system, the first 2, to denote that. We talked about truth tables, how you could find a formula in Boolean algebra and completely describe it with a truth table, because you can enumerate all of the truth values of the different variables. We talked about this handy cheat sheet of Boolean substitutions, which can be used to simplify Boolean algebra formulas. We talked about functions of logical variables, and we talked about how this can be turned into the parts of a silicon transistor in a computer. We talked about how all of the different Boolean algebra expressions can be represented just with this one, the not and logic gate. And we talked about how you could create those in a silicon chip to create a CPU only using NAND gates. Then we moved on to this topic about doing some arithmetic. Arithmetic. How does your computer add 1 plus 1? And we all agreed that when you add 1 plus 1 in your computer, oops, 1, I'm going to do it off my head, I'll do it over here. 1 plus 1, I'm going to put a plus there. And the answer for that is 0. 1 plus 1 is 0 in your computer, but you carry the 1. So that was our outcome of the way to add up 1 plus 1. 1 plus 1 is 0, carry the 1 into the next column. Oops. We had this little widget which was talking about our number representations, and I started to hint at the fact that we would be spending a little bit more time looking at binary and hex representations, and particularly just making things simple. Let's just look at 4 bits at a time, a 4-bit number goes between 0 and 15. And then if we want to represent that in a more convenient way, we often use this hexadecimal notation. And the hexadecimal notation is just taking groups of 4 bits and turning them into one single character. So with binary, we go from 0 to 1. With decimal, we go from 0 to 9 in each column. And with hexadecimal, we go from 0 to F. And then there's the old joke that, you know, you can kind of pronounce these things with, in some funny way, 76 or something. There's a joke in a show called Silicon Valley about doing arithmetic with hexadecimal in your head. How real hackers can do that. I'm sure they can't. We talked about combinational logic. What was combinational logic? It was a procedure for going backwards to find the Boolean logic formula which can represent certain outcomes that we want. So if we knew that we wanted 1 plus 1 to equal 0, we could create a truth table for that, and then we could go backwards to work out the Boolean algebra statement that suits that truth table. And it was a really useful way of doing that. Then we used the carry column as well, so we could carry the 1. 1 plus 1 is 0, carry the 1. And then we could put that together to make a half adder, which can add 2 bits together. It can give us an answer, their sum, and it can also give us the carry column for the next row. Then we realized that we needed more than just the carry the number to the next column. We needed a way to import the number from the previous column when we're doing our additions. So we talked about carry in, and it's a more combinational logic. There's a few things disappeared there, and then we made this full adder where the carry in can come from the previous column. And the last thing we did was put this together into a series of little adding machines just for one binary digit at a time, and that we can use to add up 3 bits. And this was the last slide we had last week. And we worked on a problem, something like this. If you want to add up 1, 0, 1 and 0, 1, 1, how can you put those numbers into this adder and get them to make sense? So we can put them in like so. Suppose this one's A and this one's B. That's going to be the lowest bit. The lowest bit goes into the left part of the adder here. That's 1, that's 1. A here is 0 and B is 1. Then B is 0 and A is 1. Okay, should we do it? A and B, there's 2 1s as input to this adder, so that's 1 plus 1 is 0. Carry the 1. We've got 3 inputs to this adder. The carry is just another regular 1 now. So it's 1 plus 1 again is 0, carry the 1. And this adder over here, 1 plus 1 is 0, carry the 1. Whoops, I'm out of writing space on this slide for some reason. My writing system is a little bit weird. I think there's some zooming going on in my browser, but the output of that is 0. So these 2 numbers, in fact, the answer is 000 and then carry the 1. Well, that's interesting, isn't it? That's interesting. I hope there's some folks in the chat right now, because I'm going to start asking questions of you in a minute. If we're in a number system that only has 3 bits, then really we don't understand this last one. That doesn't exist. So our answer is A plus B equals 0. And if we had this equation in any normal math situation, A plus B equals 0, what does that say about A and B? I guess just sit here sipping some coffee, and you folks out there can tell me, what does this equation, a plus b equals 0, say about a and b? Two answers there. Oh, someone's given me an answer. They are the additive inverse. Oh, that's too complicated for me to understand. Give me a simpler answer than that, along the same route. Ah, someone's come up with something. Someone says, coffee cup goes on the coaster, not on the pad. Someone says that means, well, there's two answers which are correct. It means two things. A equals B equals 0. They're both 0. But we know they're not 0. 101 and 011, they're not 0. So that can't be right. The other one was A equals negative B. Ooh, interesting. Interesting. One must be negative, one positive number. Yeah. So now we're talking about negative numbers, but we haven't got any negative numbers. We've only got ones and zeros. This one, A, what number is that? That's the ones column, that's the twos column, that's the fours column, so it's 5. And B is 3. So 5 and 3 equals 8, not 0. But our number system here only goes up to what? What does our number system go up to? 1. We've only got 3 bits in our number system right now. 1, 1, 1. The maximum number we can express is 7. So there's something funny going on here, isn't there? They have carry 1 unless they're both 0. That's absolutely true. Someone said that they're carrying the 1. Yeah, so in this, when we added them up, we did have to carry the 1. There was a 1 carried. But we've only got a 3-bit number system, so we can't do anything with that 1. And I guess this is one of the differences between number systems in maths and your regular everyday life and number systems in a computer. Because when you've got a number system in maths, if you've got a big number, say 98,762, and you add 1, you get 98,763. You can keep going higher and higher and higher in the normal natural numbers. And if no matter how high we can get, we can always add numbers to them and just keep going. But when we're in a computer or any kind of mechanical calculation system, we've got a limited amount of space to represent numbers. You remember having a little calculator as a kid and would only have like 8 numbers on the screen? That's pretty limiting, right? You can't go any higher than those 8 numbers. And that's just like what computers are doing all the time, because computers always have a fixed amount of memory for doing, or inputs and outputs for doing arithmetic. So they can only represent numbers up to a certain amount. And this leads to some interesting things, doesn't it? It leads to situations where you can add 2 numbers and essentially get 0. But it also leads to something else, which is that it's possible to take advantage of our system to do subtraction with the same machine that we've already built to do addition. So I'm thinking of this full adder as a machine, okay? It's made of logic gates. These logic gates are made of silicon chips. It's a machine. You could build it with physical objects, with wood and little balls falling down pegs or something, if you had the right kind of little mechanisms. It's an adding machine. For subtraction, we've got 2 options. I guess we could make a completely different machine just for doing subtraction, or somehow we could take advantage of this funny property of limited value arithmetic and use the full adder to do subtraction again. So I'm saying we're going to go with option 2. We're going to trick the full adder into subtracting things. So let's think about what we need out of subtraction. And I've got a bigger some bigger number systems now. We're going from just 3 bits to 8 bits. What do we need out of a subtraction system? We need to define an additive complement, or a negative number for each positive number in our system, such that when you add those two numbers, they will equal 0. And by the way, it's not obvious how to do this. There are multiple ways. That's right. Someone says to clarify, the limited value property reflects the bit limitation of the adder. That's right. In computers, anything that wants to add two numbers together is going to have a fixed number of places. You can't just, your computer can't get a 9-bit number if it's only got an 8-bit adder. A 9-bit number comes along, like it doesn't even know about it because it's only literally got 8 wires into the adder. There can only be 8 bits. Someone's putting these things in the chat. Complement +1. I don't know what that means. We have to work this out. It's not obvious how to define negative numbers, but we're going to start with this concept, which is that we need a negative number, a positive number, plus a negative number. We don't know what that looks like, to be 0. And the only way to add two numbers together such that they equal 0 in our fixed bit width arithmetic is to be carrying the 1. So you can see I've got the 1 at the top, just like we had in that last example. It's pretty funny because I didn't plan to do the lecture that way. I chose 2 random numbers and ended up with the complement. But it's had a nice start to this lecture to be able to do it this way. It's as if I'd planned it. Now, we've got that. This is the expected output we want. So let's work through it. What number plus 0 equals 0? That's obvious. We can use 0 for that. What number plus 1 equals 0? 1. Then we add those, we're going to be carrying the 1. What number plus 0 and 1 equals 0? Again, it's 1. Carry the 1. What number plus 1 and 1 equals 0? 0, but we've got 2 there, so we carry the 1. What number plus 1 equals 0? 1. Carry the 1. What number plus 1 and 1 equals 0? 0. Carry the 1. What number plus 0 and 1 equals 0? 1. Carry the 1, because there's 2 1s. And again, same thing. What number plus 0 and 1 equals 0? 1. Carry the 1, and the carry the 1 goes there. So these two numbers added together equal 0, 0, 0, 0, 0, 0, 0, 0, carry the 1. And we can now define this number 1101, 0110 to be minus 42. I'll write defined equal in our... So we already have this one. That one equals 42. And we have that one's going to be defined equal. So we're going to choose some binary numbers from our set and say those ones are going to be negative numbers. And some other ones we're going to choose and say those ones are positive numbers. Let's just have a look at what this means. I've got my handy dandy white chalkboard here, I think. Yeah, or my whiteboard. We'll go back into just a 4-bit world, I think. 3 bits is a bit too few. 4 bits is more fun. So 4 bits, 1111, that's equal to 15, right? Okay, so we've got 0. I'm going to start in the middle. 0, that equals 0, 0, 0, 0. Okay, 1 equals 0, 0, 0, 1. What number can we add to 1 to get 0? We'll start from the right-hand side. Add to 1, 1. That's going to lead to carrying the 1. 1 and 0, we need to add another 1. Carry the 1. Got a 0 there. 0 plus 1 equals 0. Oops, that's plus 0. Plus 1. Okay, same situation. Carry the 1. 0 plus 1 equals 0. So we're going to define that one's going to be minus 1 now. 1, 1, 1, 1. That equals minus 1 in our representation. Well, this is convenient. Minus 1 is just next to 0. How useful. just like the normal numbers. It sort of feels convenient that if you add 1 to -1, you get 0, but it feels like they're related anyway, because the 4-bit representation of a number was just going to tick over when we added 1 to it. And now we've got 2. 0010. That's 2. Okay, should we work out the negative representation of 2? What do we have to add to 2 to get 0? Add 0 to 0 to get 0. We add 1 to 1 to get 0, and we get to carry the 1. And we've got another 1, 1. Wow, another convenient thing. -2 is going to be right next to -1. We're just ticking down 1 bit. And I think if you'll find that if you keep going up and down, it's like counting down negative numbers and counting up in positive numbers. Now, this way of representing negative numbers, it actually isn't the only way of doing it. So it's got a name. This one's called 2's complement. Sometimes it's written this way: 2 apostrophe commas complement. And the 2 here is related to the fact that we're in a binary arithmetic. So the maximum number we can represent is 2 to the power of n minus 1, where n is the number of bits. So if we've got a 4-bit arithmetic, that means we have 2 to the power of 4 minus 1. That's the maximum standard positive number we can represent. What's that? 15. I hope this makes sense so far. Perhaps it shouldn't. If you think it makes sense, maybe you're not trying hard enough to think it through. But perhaps I've explained it so well that everyone is super clear, which is good. Get back to my slides. I have the answer written out on this slide for that -42, 1. And then we've got this picture, the 2's complement circle. So we have just as we were working out on the whiteboard there, or the blackboard, we've got our, on the inside of the circle, we've got our positive numbers and negative numbers going down, and on the outside we've got the standard positive only representation. Now from now on, when I say a positive number representation, I'm going to call it unsigned. And on the inside it's signed. And when I say signed, you can assume I mean 2's complement. The idea of how to do this kind of stuff has been worked out way before computers existed, right? Because people before computers had mechanical calculators. And just like a computer, a mechanical calculator only has a certain number of places in its mechanism for doing addition. So the idea of a something complement to represent a negative number was already worked out with a calculator that would work mechanically. And then that was transferred into electronics when people started to work in a binary arithmetic way. So if you're doing work in a calculator, you might use 10's complement, because we've got the 10's base 10 system for our regular counting. But mechanical calculators work a bit differently because of they're not constrained only to binary arithmetic because of their electronic nature. So they have a different way of working. I don't know a lot about them. They look terrifyingly complicated if you see inside a picture of one on the internet. But interesting that a lot of this stuff predates computers. It was worked out before, and then the knowledge was transferred. So we've got one representation, binary representation, but two interpretations of that number, an unsigned interpretation and a signed interpretation. Let's just talk about a few properties of this circle that might be interesting. How many positive numbers do we have? 1, 2, 3, 4, 5, 6, 7. How many negative numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we get one extra negative number than we get positive number in this system. And we get 0. So 0 sort of gets eaten from the positive side. Special number. What about the one in the middle? Because we've got now, on the positive interpretation of 8 is going to be this. But its negative interpretation is also that. So that's interesting. If we just add these two things together, what do we get? 0 plus 0. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 0 is 0. Someone's asked a good question. 1 plus 1 is 0, carry the 1. Is there any reason that the extra 1 is negative and not positive? Well, that's a really good question. And you know, I don't know the answer to that one. I've preloaded my brain this morning with a lot of answers to questions that people might ask about 2's complement arithmetic. Someone just wrote 10,000. That's true, 10,000 is the answer of 1000 plus 1000. I guess if someone wants to send me a binary number through the chat, you're going to have to use OB to start with. So OB 10000. But really it's OB 1234. Carry the 1. By the extra number, I mean we start at 0 here. We count down to -1 minuses this way, we get to -7. We count up pluses this way to 7. And then we've got a number in the middle, and it's a bit confusing about whether we should call that 8 or -8, because that number added to itself is a complement. So it's got a strange property. How come sine 7 isn't -9? Well, I suppose you could say sine 7 would be -9, but then you'd start... well, you can't actually, because -9 plus -7 would then equal 0. Supposing you called that -9, this is still -7. -7 plus -9 in binary arithmetic using the full adder would give us 0, which is not right. -7 plus -9, you know, it's absolutely not 0, it's -16. So the point of this representation is to preserve the natural expected addition of negative numbers and positive numbers. So -5 plus 5 in the ripple carry adder, a 4-bit ripple carry adder, equals 0. If we just said, okay, this one's going to be -9, then if you added those two things in a ripple carry adder, you'd get 0. Well, that wouldn't be what we'd expect. We'd expect the answer to be -16. We can't represent -16 in this system. So it has to stop there. I guess the question is, the one ambiguity is whether this one should be called -8 or +8. And it seems to me, I don't know if it's conventional, if there's some other good reason. It's got to be a good reason. Someone can do some research and tell me what the good reason is, and I'll come up with it next time. Someone says, is this like modular arithmetic? Well, in many ways, yeah. Unsigned arithmetic is like modular arithmetic. So unsigned, that gives to modular. Ooh, someone's got a good observation there. I'm just talking about the modular arithmetic point. When you're doing unsigned calculations with binary numbers, you've only got 4 bits. That will always be a modular operations, because in this case, like if you do 6 plus 6, the answer will be 6 plus 6 mod 16. Because we're always going around the circle. So 6 was a bad number because it's not going to overflow. If we do 9 plus 9, that equals 18, right? But 9 plus 9 mod 16 equals 2. So let's see what 9 plus 9 is in binary. 1001, that's 9. 1001. This is, we're doing unsigned arithmetic here, just in case you've lost the thread. Carry the 1, 1, 0, 0, carry the 1. So there's my 16s column. So we're doing the modular operation erases that, and we're left with 2, just as we expected. So unsigned arithmetic is always modular with binary. By the way, it's always, there's other, it's modular with signed as well. You can overflow and underflow, but what was this last one? Last question. Do we have some extra bit to indicate the number's sign, or is the circle exactly how computer represent negatives? This is literally how the computer does it. You don't have anything extra to say this is a signed number or an unsigned number. Wild, isn't it? Nothing, well, there's nothing particularly extra, nothing built into the CPU to say these numbers ought to be signed, these numbers ought to be unsigned. Here's a quiz. Are these numbers negative or positive? Negative or positive numbers? Someone says that the choice of whether it should be +8 or -8 is just convention. Someone's got an answer. They're saying this one's negative, that one's positive, that one's positive, that one's negative. Ooh, someone's got a question. They've returned a question with a question. They said, are they signed? Because actually I haven't given you enough information to tell whether they should be negative or positive numbers. There's 2 of them, which could be a negative number if they were being represented in 2's complement and we decided that they were signed. And the way you can check that is whether the highest bit is 1. But I haven't said whether they're signed or unsigned, so you can't really tell. A bit of a trick question, right? But the thing to remember here is that signedness and unsignedness is just all about your interpretation of the number, because the ripple carry adder doesn't care whether numbers that it's getting are signed or unsigned. It's just a machine cranking them out, adding 2 bits together, and our interpretation can change depending on whether we want to be looking at signed numbers that might be negative or numbers that are being added together that are positive. Also, if we want to subtract one number from another, that means making them negative, because if we wanted to, so suppose I had a number 9 and I wanted to decrement it, like I'm doing a loop or something, I want to do 9 minus 1. Well, what's that? 9 plus minus 1. So we need negative numbers to do decrementing of things in our computer. Okay, now we're making a CPU out of these things. Simple ALU. So what is an ALU? An arithmetic and logic unit. And it's a part of a CPU that is going to do some of the operations that we've already talked about. And the point of this slide is to say that when you know how to use these logic gates to create circuits that can do logical operations, then you can create these mechanisms for calculating multiple operators at once. So this little calculator, this is designed by friend of the course, Uwe Zimmer, from a previous iteration. A little toy arithmetic and logic unit. It's got two inputs, AI and BI. It's got a carry in, it's got a carry out. It's got a result out, answer out. And then it's got these other things here, op 1 to 4. What does that mean? Well, the op 1 to 4 make this ALU do different things. So when op 1 is active and the other line inputs here are 0, then it turns into a ripple carry, into a full adder. When op 1 is active, it turns into an XOR circuit. When op 3 is active, it turns into an AND circuit. When op 4 is active, it turns into an OR circuit. So Uwe has put together these logic components and made something which can create 4 things at once. Excuse me a minute. Hello. Good, thanks. Sorry, I'm in the middle of something. I can't take your call right now. I thought it was a package. Well, excuse me. Here I am. We got 4 inputs here, each of which is turning this little machine into a different kind of arithmetic or logical operation device. So we can actually use logic components to create these different machines inside a computer and reuse parts that might have been wasted. We're not making a machine just for adding, a machine just for doing ANDs, a machine just for doing XORs. There's one big kind of machine which can do all of these things at once, and you can change it in different modes. So that's what an ALU is doing. And this is just going to deal with 1 bit. So that's why it's called ALU slice I. It's just 1 bit of a ALU circuit. Are Uwe's raw LaTeX files available? I don't think he made them in LaTeX. They were probably all drawn up in Adobe Illustrator. He's an excellent PDF artist. So, the last little topic here that leads us to the end of the lecture. Sequential logic. So we're going to talk a little bit about memory now, because so far we've talked about systems that are taking 2 things, 2 binary numbers, and applying some operation to them. But it doesn't have a memory, does it? It's kind of has no sense of state. It can't remember anything. If you do something in one step and then do another operation, there's no communication between those steps. So we do need some kind of feedback in our circuit to communicate between steps. And that's what we're going to get to now. So the idea here, I'm just going to go to the circuits. The idea of this circuit is that the outputs are going back into the inputs, which gives us a kind of remembered state of previous activations. And this is a really interesting little circuit. It's called an SR latch. And I think I would like to make one now in DLS and show you what it can do. So I'm going to need 2 NANDs. There we go. And I'm going to need 2 outputs. And I'm going to need 2 inputs. So I'm going to put my inputs into that NAND, 1 input into this NAND. Output goes straight to the output there. And then I'm going to do this kind of cross-wired feedback. Okay. So here's the trick. When this input at the top goes to 0, the output at the top goes to 1. And now no matter what I do with that input at the top, that one stays as 1. When the output at the bottom goes to 1, no matter what, when the output at the bottom goes to 0, no matter what I do with it, this one at the bottom goes to 1. And I can do that again. I can store a 1 at the top and store a 1 at the bottom. This seems like a very simple little device. What it's called is a set reset latch. So that's going to be called the set port. This one's going to be called reset. Whoops. That one's going to be called Q, and that one's going to be called not Q. That's pretty cool. I should take a sip from the cup. Now, this is very simple, but you can start to see how we would make a kind of memory, because once we activate this top output, it stays set no matter what else happens to this input. And once we deactivate it, it stays unset. When we're talking about binary numbers in computers, we often use the word set to mean turning one binary digit to a 1 and unset, turning it to a 0. In other words, to turn it to a 0 is clear it. So set, turning it to 1, unset, turning it to 0, or clear, turning it to 0, or reset, turning it to 0. So we've got a very fun little device here. Should we just have a little look and see how it works? When I've got 1 and 1, those two lines are, well, this line's active. Let's not talk about this line for the moment. We know that a NAND logic gate is active in all states except the state where both of its inputs are 1. So this is the only state where it's not active. 1 input, 0 output. So if I turn that to a 0, no matter what else is coming into the other leg, the output here is 1. So that's 0, that means that the output's 1, that means that this Q output is going to be set to 1. Now let's talk about the other one down here. Supposing this input's 1 and this input's 0. Now this is positive input there. That one's still 1, so we've got 2 1 inputs, and it's negative out the bottom. So then if I turn this one to 0, I'm doing the same thing to the bottom NAND. It's now got a 0 leg. It means that no matter what the case is with its top leg, it's going to output 1. And because this one is still got a 1 input, that one will start outputting 0. So by changing the reset to 0 and activating the output of this lower NAND gate, I'm deactivating the output of the top NAND gate. Someone says, what happens if it's first initialized? Very good question, but the answer would be that you don't know what the output will be when it's first initialized, so you would have to set it into a certain state or reset it. So if you just turn this thing on with voltage going into the top one and voltage going into the bottom one, you're not sure whether Q is going to be 1 or not Q is going to be 1. It's random, yeah. I mean, I guess I don't like to use the word random. I like to say that it would be not determinable. You don't know. One of these NAND circuits might be faster than the other one. In DLS, the sandbox, this is not real. It's not real silicon. But if we made it, I've got a link to a video at the end you can watch where there's a video of someone doing this with a real circuit, and they make the point that it might be a different output depending on factors which we don't understand and can't track down. Now, so there are 4 possible input combinations with an SR latch, and in this case we're denoting both of these inputs as sort of negatives. That one's actually called not S. Set, not S. And that one's called not R. You can also make a SR latch with NOR gates, and that ends up with sort of the flipped or the inverse inputs, achieving the same outputs. So if they're both 1, we're keeping the current state of Q and negative Q. If we drop the negative S input to 0, we set Q to 1. If we drop the negative R input to 0, we reset Q to 0, just as we talked. And then what about this last one? What if they're both set to 0? Well, if you set both to 0, you end up with both Q and negative Q being 1 at the same time, which is not a problem in and of itself. But if we were using this in a greater design, we might find that we wanted to use the negative output, and we wanted to rely on the property that Q and not Q were always opposites. So the fact that setting both inputs to 0 kind of means that we're ruining our assumption about our own circuit. We also have a problem in that if you go from 0 to 0 to this other state 1, 1, I can't do it here because I've only got one mouse, but if we turn both of them on at the same time, turn both on, then we're not sure if this one happens to go on first, minus Q will be set. If this one happens to go on first, plus Q will be set. But if we're trying to do it at the same time, one of them is going to win, and we don't know which one it is. So if we're in this state, the forbidden state, if we're in this state and we go straight to this state by turning on those two lines at the same time, we don't know what the knowledge of Q is. We don't have any knowledge of what the effect is. It's indeterminate. We can't tell. It's called a race condition in that case. You might have heard that before in computing, in concurrency. We've got two circuits here. We're turning them on at the same time, and the actual output is going to be determined by knowledge that we don't have. It'll be knowledge about which of those NAND circuits is faster, or which wire is shorter, or something. I don't know. There's no way to know from our position as a programmer or a designer. So that's the SR latch. I've done a little demo. We're going to actually show some more complicated latches. A few problems with the latches. There's other solutions for more complicated ones. This one's called a gated D latch, where you've got another layer of NAND inputs, and that kind of abstracts one step away from those direct inputs. We've still got the latch circuit in the middle, the very important one, and the C line here, I think, is going to determine when you're allowed to set the latch. So I think if you turn on C, and whatever you set D to will set Q, so D and Q will end up being equal while C is turned on. And then when you turn off C, no matter what you do to D, it won't affect them. So rather than having a set reset, we've only got one. We've got one data input, which will just set the other outputs. So as an exercise for the reader, you can take this one and go and implement it in DLS and see that it works. And if I'm wrong about how I explained it, you can tell me in Piazza. Even more complicated one. This one's called a JK flip-flop. And again, you can see there's a few, there's a SR latch right there. And we've got another SR latch here, so it's got a 2 SR latch design. It's giving us a few more inputs and a clock. And the idea with the clock is that on a certain change, 0 to 1, it would allow you to set the latch. I haven't actually tried this one in DLS, but maybe we should make it and have a try. I might have a try after the lecture. if anyone is still around. So this one lets us use a clock signal to set the outputs, which will then stay locked in. Definitely a more complicated circuit though, but this is the one which is probably more common. The SR latch is the really simple version of the same thing. So what do we? Oh, you can also make these things in Minecraft if you want. There's a link to a video in the slides. What do we use these things for? Someone said in the chat already, we can use these things to store a number. Make what we call a register in our assembly programming world, the CPU world. A register is a memory device for storing one number with a certain number of bits. So we can store multiple bits at once by getting a D latch like this. There's the C line in, the enable line, and all of the data inputs and the outputs for each one. So when we want to use this design, we would set all of these lines to represent the binary number we want with voltages, 1, 1, 0, 1, 0, 0, 1, 1, a nice negative number if we're in a signed arithmetic environment. Then as soon as we hit C, enable that line, those numbers will propagate through the system. Great. And you can read the output anytime you want. You can read it without messing things up. So you can see what the Q outputs are doing. Then if you want to change your number, you're going to have to change the D inputs and then set the enable line again, which will overwrite the data stored in that register. Another thing you can do with a latch is make a counter, which is cool. So in this version, the outputs are going to the input of the next one. So we can start the counter by setting this one to be 1, and then if we sort of clock it, every time we put the enable line up and down, that bit is going to propagate through the system, through each little latch, and then at the end it'll sort of drop off the edge. Who knows? We could design it so it goes back in the start and starts around again, or it could go somewhere else and give you a signal. I've got to the end of my counting, and we can have a reset line that can reset all of them together, so that we can stop our counter. And actually, counters are a really useful thing in computers. They're used all the time, and you will be using them in the in the course. Someone just said a hardware level race condition will be hard to debug. Yes, impossible to debug. So you have to design your hardware so that you never get into a race condition. Ooh, we've done a lot of complicated diagrams in the last few minutes. And maybe you're feeling a bit lost, but the bigger point here is that these are all just physical little machines in your computer, little mathematical machines. There's no magic here. You've just got billions of little machines doing what they do, working all together, hooked into each other. And the concept of this lecture this week was to give you an awareness of how you can go from what you've learned about Boolean algebra and maths into something which could actually calculate things automatically for you. It can add numbers together. You can count. You can store a number. You can add a number and a negative number. So you can subtract now. And you've got an awareness of that whole pathway from Boolean logic and from silicon circuits to something that you might start to use in an algorithm. I want to point out before I stop the proceedings that there's some videos here by a person called Ben Eater on YouTube. Logic gates, SR latch, D latch, D flip-flop, JK flip-flop. Ben Eater a few years ago went on a mission to demonstrate how these things work with physical hardware components. So he's using a chip that would contain some NAND circuits, sort of a simple, quite a chunky looking chip, but it has a simple circuit inside that will give you a couple of NAND inputs and outputs, and use that to create an SR latch, and use it to create a D latch and a flip-flop and a JK flip-flop. So those videos are really, really interesting. They're quite long if you watch all of those. I think it's about 2 hours of video there. Each one's about 20 minutes. But if you really want to understand how these things work and see how it works in hardware, watch those videos and then go to a electronics store, get some logic gates and plug them into a breadboard and do some experiments. It would be educational, I'm sure. Now, questions, that's the last bit. I think you can, for those of you who have a 10 a.m. lab or another lecture to go to, head on off to your other lecture. But let's make something complicated. Make a JK master slave flip-flop. I'm going to make 2 windows here. By the way, I don't think I've ever done this, so, or maybe I did with, I just can't remember. I can't remember ever doing this before. So if it all goes wrong, there we go. Will we need to know how to make the circuits from memory? If we power off the circuits of the SR latch, will it lose its memory? Absolutely, it will. It will lose its memory. So the 0, 0 input, it's got this forbidden term, like you're not going to go to jail if you set an SR circuit to 0, 0. In fact, I did right in front of you. The only thing that's bad about it is if you expect to know what the output will be if you then go to 1, 1. So 0, 0 to 1, 1 is you just don't know what the output's going to be. So if you turn off your device, you have to initialize it, set it into a known state by putting 1, 0 input or 0, 1. And then it will be in a known state after that. The unknown part is only going to affect us if we... I want to move. Okay, right click is move. The unknown state's only going to affect us if we have our system turned on and we expect to know what the output's going to be. So I need 4 rows of NANDs for my JK flip-flop. Someone else asked if you have to make these circuits by heart, or by memory, sorry. By heart is a kind of a nice English idiom for something being by memory. What? It's got 3 inputs there. Well, that's not right. NANDs only have 2 inputs. Sometimes Uwe's diagrams are so beautiful, they may be wrong. JK flip-flop. By the way, if you Google for something, I'm not sure that it's always going to be right, so. I'm not an electronics engineer, so I'm confused by what they mean by having 3 3 inputs on a NAND chip. Maybe someone who is an electronics engineer can sound off in the chat and tell me what it is, what I'm supposed to be doing. There's my SR gates. There's an SR latch. Some basic electronics knowledge is available on Wikipedia. The gated SR latch, gated D latch, Earl latch, D flip-flop. Okay, so far so good. Positive edge triggered D flip-flop. Okay, there's a diagram which doesn't have mysterious 3 inputs. There's 2. And it uses NANDs, that's good. I'm going to follow this one. Not the weird one with 3 inputs. And we can work out maybe what 3 inputs means at a later time. Okay, so that one, I'm going on the second layer back. And those ones get connected only here. So this one is another SR circuit. So now we've got our two, there's an SR latch, there's an SR latch. This whole thing is would be the gated D latch. I'll just go back to the previous page. Yeah, that's the same thing, right? That one, top one, is connected to the input of the bottom one. So this much is a gated D latch. I guess we could start with that. The third input to set and reset. Maybe, I just don't understand the diagram. Like, NAND is a logic operator that's binary. A binary operator has two inputs. When you put a line right in the middle, does it mean it's connected to both or what? I don't know. Mysteries to me. So we'll deal with the gated D latch to start with and just see what this will look like. Okay, so we connected D there, and now we connect C to both these ones. Okay, and I'll just zoom on this a little bit more. So that top one is D, and that bottom one is C. So I think when we operate C, anything we do on D is going to be reflected in the output. So this is the D input. If I turn that to 1, we get a 1 here and a 0 there. Turn it to 0, we get a 0 here and a 1 there. If I turn off the C input, it doesn't do anything. So that's our enable input. Okay, so we got half of our two-layer latch here. Let's keep going, following the Wikipedia design, and then we'll compare it with what Uwe has provided for us. Whoop, I'll zoom out a little bit. That one connects to there. So that's the Q output. We're just taking one output from our this gated D latch. And then in this design, there's a couple of knots on as well, which I think are going to be useful. Possibly Uwe's design is just let us do this without having extra knots. You know, you can make a NOT gate out of a NAND gate by tying the two inputs together. Okay. So we've got a D latch here, but it's got a flipped clock. So when the clock line is low, I'll turn that to C. Clock, data. I presume that D is for data and C is for clock again. Like, it runs the end of my electrical engineering knowledge pretty quickly in this in this game. When the clock is 0, whatever we do on that data input, I'll make this bigger again, sorry. Whatever we do on that data input is represented in this output 4. Okay, when clock is 1, I think I know what's going to happen. when clock is 1, it's going to propagate it through to the next input. So clock 0, we set it. Clock 1, it goes to the output. So if I set that to 1, okay, set that to the clock to 1 there, we change that to 1. If I go 0, 1, it goes to the output. 0, 1, 0, 1, 0, 1. So if this is a clock line is a kind of circuit which is going to go up and down and up and down. If I just go back to my drawing slides, sorry, there's a multiple Charleses in the background. Clock line is going to go like this, hopefully in a kind of nice square wave pattern. We look at this more a little bit later in the semester. Woo. Oh. That's 1 and that's 0. And 1, by 1 I mean a voltage, right? It could be 5 volts, or it could be 3.3 volts, or it could be 1.5 volts, or it could be 0.5 volts, some kind of voltage on a wire, and then 0 is going to be 0 volts or ground. So that's what a clock line is going to do. Uppy, downy, uppy, downy, uppy, downy, continually and continually and continually. So that means that this JK design, as the clock goes 01, 01, it takes an input at the O stage, stores it inside, and then when it gets back to the 1 stage, it comes out. So here we go, we're at 1, so the output is being displayed. We change to a 0, store the input, change to 1, and it ends up on the output. And then nothing changes after that. Put a 1, there we get the output. 0, storage, output. 1, there's not that much you can do with these things, they're only binary, so storage, output, storage, output. What do they say about here? A master-slave D flip-flop is created by connecting 2 gated D latches in a series and inverting the enable input to one of them. Yeah, so the first latch, latch 1, is controlling the output, forcing it to hold its value whenever the other one's enabled. And this would be a positive edge triggered D flip-flop. Cool, T flip-flops. There's so many flip-flops here. JK flip-flops. Oh, I see. So this one's just got a data line. I guess the JK flip-flop gives you the set reset line. So that would be more useful in that counter, for instance, where you wanted to be able to reset everything at once, not just change to a different input. And then you start to see diagrams like this when you look at these things in electrical engineering. There's the clock, up, down, up, down, up, down. That's right, yeah. So the clock line there is making the change reflecting the inputs. So if you're in this example, that's going to be J is the set line and K is the reset line. So when the clock goes up, if J happens to be positive at that stage, you can see it's changed to positive before the clock goes up so that it's ready. Then at that stage, the Q output will be 1 and not Q output will change to 0. Then somewhere in between, the clock is going down. We change that to low, we change K to high. Nothing's changing so far on the input to the outputs of our flip-flop. But then when the clock goes high again, on that's what we call a positive edge, where the voltage is rising at a certain time. That triggers the flip-flop to look at its inputs, and the inputs are then reflected on the outputs. So as soon as that clock goes high, it allows the reset input to change the inputs, and then we get Q going low and not Q going high. All right. Well, I think I've gone over time by enough minutes today. These things are more fun to understand when you try it yourself. So do try out opening up DLS, give it a go, and prove that they work the way that you think they work. Yeah, I think that those extended designs would avoid the race situation. That's true. Someone is suggesting in the chat. Folks, it's been a good day talking about digital logic. We're going to go on to the next topic next week, starting to talk about machine instructions and how they relate to the assembly code that you've started to see in your labs. So for now, I'm going to say goodbye, and I will catch you folks on Monday. See you later.